Thank you for the introduction, Dev. I'm a PhD student at Arizona State University, and I'm here to present my work on Everyone is Different, client-side diversification for defending against extension fingerprinting. In short, it's cloaking browser extensions. This was a cross-institutional effort between Arizona State University, Stony Brook University, and North Carolina State University. So, browser extensions, they are third-party programs used to customize the web browser. I'll bet most of you in here probably have at least one of these up there installed, considering that across just these listed here, there's over 55 million users that are currently using one of these. Now, this customization that you have to web browsers comes at a cost. Extensions are granted more privileges than just a standard web page. And with identification or detection of specific extensions, you have this cookieless identification across browsing sessions that's possible. Now, inferences based on a specific extension when it's detected you can have additional inferences made based off a specific extension like Honey, for example, which is a coupon clipping extension. Customers that come to your website with that installed might be more price conscious. Similarly, LinkedIn recently was found to be detecting over 100 different extensions of the people that come there, mostly focusing on those that violate the terms of use. Now, how do we prevent this? Well, it could be prevented through the web browsers. They're definitely taking steps to do this sort of stuff. And it could also be the extension developers could help by reducing how much they change the DOM or how much they use web accessible resources for detection. However, we decided we didn't want to wait for that. We wanted something now. And so we created CloakX, which is an extension cloaking tool that uses static and dynamic analysis to perform client-side modifications without having to modify the browser and without requiring extension developers to modify their code. Now, for extension fingerprinting, the fingerprinting is not actually something intentionally offered by browsers. It's supported through side channel attacks. For example, at CodeSpy in 2017, there was a paper where they presented the use of web accessible resources to fingerprint various extensions. And a little bit later in the same year, Xhound was released and for DOM fingerprinting, which is tracking the changes between the DOM when the extension is installed. So for war fingerprinting, web accessible resources are uniquely identifiable resources that extension developers deliberately expose to web pages. War fingerprints or web accessible resource fingerprints. In our research, we found 16,479 of the 59,000 extensions that we downloaded were detectable using web accessible resources. And 50% of the top 1,000 extensions were detectable using the same method. For DOM fingerprinting, we used Xhound, and it exercised the extensions and tracked DOM modifications, both with and without the extension, and was able to create a fingerprint from that. And we were able to create fingerprints for 5,323 extensions. So for detection, it's this fingerprint that we create a link between the actual fingerprint that's created and the specific extension that allows us to detect users. Now, we wanted to come up with a way, or we came up with a way in the paper to kind of talk about this with some terminology, and one of those is anchor prints. Anchor prints are created because there's a unique anchor that the extension uses to tie it to the web page so that it can access any elements that it's dropped onto the page. WARs, IDs, class names, and custom attributes are all examples of this. Take, for example, Save to Pocket. In that extension, there is an image tag or a SVG that's dropped onto the page with a specific class. And with one line of JavaScript, you can search and find this class and know that the Save to Pocket app is installed on the user's machine. Similarly, we have Structureprints, which use the structure of changes an extension makes to a web page. For example, with the Google Calendar extension, it injects an anchor tag and an image tag, each with specific attributes that no other extension adds. So just by having these on the web page can be relatively certain that that extension is installed. So the last one that we look at are behavior prints. And these are targeted, kind of a subset of Structureprints, where it targets the extension's actual behavior. Take, for example, the Grammarly extension. It injects a green image into a text area, like you see below. And the web page can just detect that this is injected into the page. And this is normal standard behavior that we're expecting, what we expect Grammarly to actually do, that it's detecting. So before we can talk about how we go through the cloaking process, need to kind of take a step back and talk about how these work, how web extensions work in the web environment. So looking at a web page, it's given its own JavaScript execution environment, it's got its scripts, document object model, HTML, and then we add in extensions, and there are these additional environments for every extension that's installed. And starting with web accessible resources that I've mentioned before, those can be accessed by the web page and loaded directly in that execution environment. Another thing that extensions have are background pages, where they have scripts that are loaded into this separate execution environment where they can run with additional privileges. They can access the local machine and access local files and other access with the operating system. Next, we have content scripts. Content scripts stand somewhere between the two with a little bit of elevated privileges, but mostly they're there to interact directly with the DOM and add, load, change things that are actually inside the web page, the underlying web page. So our goal with CloakX was, despite there being this fingerprint for, say, Google Translate, was to break the link between the two so that the cloaked extension couldn't be detected by an underlying web page. And the way that we did this is we went through and we renamed and discovered the WARs, the IDs and class names, with the idea of renaming these anchors so that we could anonymize the extension. And then we would go through and find all of the references to these WARs, IDs, and class names and rename those within the extension itself. On top of that, we used random insertions to prevaricate and to confuse an underlying web page so that it would be harder to determine which extensions were installed. So the cloaking process in general works. We run it first through Xhound. We get the DOM objects and the IDs and the class names, and then we run it through WAR randomization, which is where we discover the WARs, the web accessible resources, we rename them, and then find all the references and replace them. That's all done statically. Now for droplets and style, droplets is a term that we came up with. This is the case when you have something that comes from the content scripts and it's data that comes from the extension but is then loaded at execution time, dynamically injected into the web page's DOM, via the web page's DOM. It's a dirty, little insecure process or very insecure process, but it's also clear why the extension developers want something like this. They want to be able to have code that's running natively in that JavaScript execution environment on the page. And we need to make sure that we rewrite all these instances when this is used so that the extension still functions properly. To do this, we used Taegis, which is a type analyzer for JavaScript, and we added a little bit of taint analysis to it. And that was to help us identify the IDs and class names that were interacting with the DOM. And then we would rewrite these. The last piece is we would add the dynamic proxy that we called Droxy. And Droxy basically sits in the content scripts environment and intercepts any requests to the DOM. And if there are ID or class names, it renames those. In addition, it injects random IDs and class names that do not interfere with the operation of the web page, but also help obfuscate its fingerprint. So here's an example of a cloaked extension. This is the SEO bar. And you can see the before above and the after it's cloaked below. And it's got the different IDs and class names are all randomized to new values with differing lengths and differing values. So how do we evaluate this? It's not the most straightforward thing. First is to kind of think about what did we want to evaluate. And we wanted to capture functional equivalence, meaning the extension, the original extension before, is it operating in the same way as it is after? The problem being that we have 18,000 different extensions. So we came up with kind of a two-pronged approach with our functionality experiments. And the first was a low fidelity, an automated process that would go through all of the extensions that we modified and look at them before and after in an automated way, and then evaluate whether there were any differences in the errors that were thrown by them. For the high fidelity testing, we randomly sampled 150 extensions and went through manually exercising them as vigorously as possible, while also evaluating whether the user experience had changed from the original to the modified extension or the cloaked extension. For the second part that we tested were detectability experiments. Were we able to detect these cloaked extensions with anchor prints, structure prints, or behavior prints? So for the low fidelity testing, we tested 18,937 fingerprintable extensions. And for WAR fingerprintable, 99.0% of them passed the functionality testing. For DOM fingerprintable, 98.7% passed. And for WAR and DOM fingerprintable, 97.9% passed. For the high fidelity testing, as I said, we tested 150 different extensions. For WAR fingerprintable, 50 of the 50 passed. For DOM fingerprintable, 48 of the 50 passed. And for WAR and DOM fingerprintable, 47 of the 50 passed. Now, we had some issues with these, and one of the most common issue with the ones that failed the functionality test was actually remote code loading. So these extensions will actually load code remotely from, say, their web server and bring it in, and that piece of code is still trying to access the original IDs or the original WARs. Some of the extensions had hard-coded values. For example, our Droxy promotes itself to be the first content script that executes so that it can intercept everything that's sent. And in one of the cases, the extension had hard-coded which spot it was in the list of content scripts. And then just some limitations with Droxy where we could add additional functionality to support recursive iframe sourcing, for example. So for detecting anchor prints, for going through and detecting everything, we ran this on 17,678 extensions and found that the cloaked extensions weren't detectable. However, 96 of them did not maintain equivalent functionality, and so we counted these as actually being detected. For structure prints, 5,311 of the extensions were tested with fuzzy matching, and the first set used the entire data set, which was tags, attributes, and text for the DOM changes, and we were able to detect 4.2% of the cloaked extensions in this case. For tags and attributes, it went down. The fuzzy matching was faster, but we weren't able to detect as many of the cloaked extensions at 1.8%. And then for tags, 1.7% were detected. Now for the last test of behavior prints, this went kind of beyond our threat model that we described, but we wanted to see how well an advanced and highly motivated adversary that was spending the time to look specifically at extensions and devise ways of identifying these extensions from a web page could do. And we ran these. We selected 10 of the most popular extensions, and 7 of them were detectable even though they were cloaked. Randomly, we also selected 10 extensions just from the entire population and found that 5 of those were detectable even though they were cloaked. So in summary, extension fingerprinting is a real problem. All of us have extensions. We'd all like to maintain some of our privacy. We were able to successfully perform late-stage customizations on browser extensions and break the extension fingerprint link. And then for cloaked extensions, 99.9% were undetectable using anchorprints, and 98.3% were undetectable using Structureprints. Thank you.
All right.
Hi, Ben from CISPA. One question that came to mind. So we have like these extensions that have inject elements that have a class, right? So with a class typically comes some CSS properties. Have you kind of looked into whether if I can identify that there is some random object that I did not inject myself as the website operator into the page, just look at the class, create an element with the class, and then read the CSS properties of that class to then maybe re-identify an extension?
We also altered everything through the CSS as well, okay. If that's what you're, if I'm understanding your comment or question correctly. So we tackled all that, and to actually be sure that we were getting everything, we would mock up, like a little sub-environment so that we could make sure that we selected through and we're gathering all the elements. But yeah, I don't know, am I getting...
I mean, you still, it's like for Grammarly, you still need to kind of have that green icon thingy, right? And that's styled somehow. So if I know that there is something in my page, which I don't know what it is, but I know that the style is very much similar to what is typically the Grammarly icon, could I use that information to infer that you have the Grammarly extension installed?
I mean, you could use the information, but it would all look different if you were looking at it. So if you would have to have some kind of human aspect there to know that it was a circle icon, or that the base 64 mess that they send is actually that icon. And then, but they've all been renamed through there, so you'd have to find, maybe some kind of attribute matching or something like that on the CSS.
Okay, right, thanks.
Hi, Tom Moore, Oracle. So I have to ask, is the cloak itself cloaked?
In the paper, we talk about that. We did some tests on the cloaking itself and weren't able really to devise a method that it was. But even if it was, with more people using it, then it's more anonymized because it's all looking the same.
The Tor argument, yes. Thank you very much.
Yep.
I'm Jitin from IIT Madras. So my question is highly related to the first question. If I create a hierarchy of classes, for example, for an element, the number of classes is still detectable, right? So if I create a hierarchy where the number of using number of classes per element and their hierarchy, the hierarchical elements, can I detect the extension using such a fingerprinting? I'll reframe the question. So if I have a unique hierarchy of elements along with the number of classes, because the number of classes remain the same even if you rename the class, right?
Right.
So can I use that as a detection method?
I mean, it would be possible if you took the count, but it'd be very fragile, right? So, I mean, it's real easy to add additional classes that, say, aren't used, or there might be, even when you load, you have something that gets activated in a different way.
Do you add any classes to change the structure?
I don't remember.
Okay. Thank you.
Yep.
All right, let's thank the speaker again.